right, welcome back. It's me again. I've talked about the research opportunities if you want to get involved in creating next generation of AI hardware, in particular with a memory-centric focus, please reach out. So it's my great honor to introduce our speaker. But before that, I just want to throw this cartoon out from the World Economic Forum, right? So you have been sending out emails, right, dealing with the social media information every day. We are really generating a data deluge, right? So we have an estimate of over 100 zettabytes of data, right? It's equivalent to, if you're not familiar, it's 1 trillion of gigabytes, right, per year. Generated this year, projected, and going into the next decade is going to be more. So how do we handle this large amount of data to fuse the next generation of innovations, unlocking new application opportunities? We have Mr. Deepanshu Datta today. He is the vice president of the flash memory technology in Western Digital, probably one of the most famous memory and technology providers in the world. So he will really introduce you to this magical world of flash memory and how it is relevant to you folks who may be interested or even thinking about entering into this field. I will hand over to him. Thank you for visiting us and giving this seminar for our freshmen.
Sure, thank you, Professor. I got it. Thank you. Yeah, I used to be young back in the days, not anymore. So let me start. First of all, happy Valentine's Day to all of you. It's a happy day for everybody. Hope some of you have good dates tonight. So, all right, let me start with getting back to technology stuff. I'll be talking about NAND flash memory and how we have been innovating to keep up with the world's storage needs. So Professor talked about the great amount of data creation that happens on a daily basis, and I'll also touch on that. But that data needs to be stored somewhere for you to make use of it. So that's what NAND flash technology does. So I'll talk more about that as we go through the talk. First, before I go to the talk, I want to just introduce my own personal journey, because the purpose of this course, I believe all of you are freshmen, or most of you are freshmen here. The purpose of the course is to encourage you to get into semiconductor chip area, if you're interested, right? If you think this is the area for you, we want to encourage you to look into the opportunities here and show you how these things are done. So I wanted to walk you through my own personal journey, how I got into this area. So I grew up in India, and I did my undergraduate from Indian Institute of Technology, Delhi, in engineering physics. And at that time, I don't think I knew much about chips or semiconductor, et cetera, those kind of things. But as I went through this undergraduate course, where all of you are right now, I realized that, hey, I really like semiconductors. This is the future. Chips is where everything that we do, all aspects of our life are driven by chips. No matter what you touch around you, this has a chip inside. This has a chip inside. This has a chip inside. You go on and on. So I realized that this is the future, and hence I wanted to be in that area. And then I looked for opportunities to come to the US to work on cutting edge technology in that semiconductor space. I was lucky enough to get a position in University of California, Irvine, where I studied in material science and engineering, and I specialized in nanoelectronics there, and that's when I moved more closer to chips, I would say. And then after that, I was lucky enough to get a job at SanDisk. I actually went to the career fair in UCSD, not in my school, but an hour drive, and I happened to find a job there, so I made my resume there, got called, was lucky enough to find a job there. And then when I started the job, actually it was a semiconductor company, but my role was different from what I do today. But I just wanted to get into the space, and I got into it, and I had my managers who were, fortunately for me, recognized my potential and moved me into an R&D area over time. So, and then after that, the SanDisk was acquired by Western Digital back in 2016. And since then, I've been just working there, and I've been just growing through the ranks and expanding my area from a memory cell technology development all the way now to I handle the whole technology development team. And this is just my family. Actually, I met my wife in my grad school. I think some of you might meet your future mates here as well. Maybe today is a good day, Valentine's Day. So this is my family. This is my wife, Bridget. This is my son, Mars. That's me. And my daughter making a silly face. And I can't forget my puppy. Her name is Marble. So that's my family, and that's my personal journey, how I got into this space. But really, one thing is that life unfolds in unexpected ways. You just need to have a broad vision of where you want to be, what you want to do, and be open to change. And things unfold. But as long as you know what you really want, or at least broadly speaking, I think you'll get there if you stay passionate and you stay motivated to your mission. That's what my experience tells me. All right, so moving on. So, you're sometimes a little bit down, and then you get to your home or get to your dorm, wherever you live, and you want to see some funny videos. It was a bad day for you, and very often you'll run into a cat video on a YouTube or something. And sometimes you think, hey, how cute these videos are. How can we survive watching these videos? Well, that's not a problem that I deal with. We deal with the problem of how will we store these videos? So that's what the business we are in. So Western Digital, introducing our company, basically our job is to store all the data that the world produces, in a nutshell. That's what we do. And there are two forms of storage in which Western Digital operates, which is where most of the bits in the world are stored. One is hard disk drives, HDD, and the other one is NAND flash memory. And I'm going to be more focusing on NAND flash memory because that is more closer to semiconductors. So Western Digital has about 50,000 employees and offices spread over 11 countries, headquartered in the US, in the Bay Area, San Francisco Bay Area, where I come from. But we have major offices in Japan, India, China, and more. And the products, I think some of you might have seen these brands if you shop online or you shop in some consumer electronics store. SanDisk is a very popular brand. I think, actually I have some of SanDisk USBs today. I might have some couple of trivia along the talk. So whoever answers it, you have a 16 gigabyte USB coming your way. So SanDisk brand is very popular, and we have a professional SanDisk brand which goes into higher end products. Then we have WD brand and WD Black, which is very famous in gaming. For those of you who are into gaming, you might be familiar with this name. And these are the visualization of how those products look like. And these are the spaces we operate in. So data is created in everything, right? Game, pictures, smart cars, smart homes. Everywhere is data. So all these areas of data creation is where our devices are used. Gaming, camera, PCs, cloud, phones, automotive, and IoT. Yeah. So that's just the introduction of the company. Now, we have been fortunate enough as a company to have many Purdue grads in our company. And, oops, what happened here? Sorry. Okay, sorry about that. So we have been fortunate enough to have multiple Purdue grads in our company. And these are just some of them who work close to the technology area I am in. But of course, we have many, many more. So these are some of the ones who have graduated from here, and we are lucky enough to have them, and we hope to have more of them in future. All right, so now let me jump into the talk. So I'm going to talk about data growth, which Professor touched on. I'll show some charts there as well, the exponential growth of data. Then I want to talk about how flash memory has been keeping up with how storing that data, right? So data is created, but we need to store it, and that's what flash memory has been doing for more than 2 decades now. And then I want to go into how we did that, right? How did this exponential growth of data, how did we increase the exponential capacity of our drives to store all that data? And finally, I'm going to touch on future of the flash memory, where we need a lot of innovation, a lot of challenges still there, and we hope some of you come to our office, come to our work in the broader industry to solve these challenges. I'm going to talk about that at the end. All right, so data growth. So this is a chart showing how the data has been growing between 2019 and including some projections all the way to 2026. So it's an exponential, right? You can see exponential growth. If we plot this in log scale, you will see it's a nearly linear function. And the data is created in multiple spots. So endpoint are the devices where, let's say, the things in your hand right now, laptops, that's a data creation. When you're writing today, you're creating data. Of course, all of you have smartphones, you have cameras, so gaming, all these are data creation devices. And that's where majority of data has been getting created in the past. But if you look at the future, majority of data is actually getting created on the cloud. So in the cloud, most of the data that you're even producing in your laptops today, most of you probably have Apple Cloud, AWS, Google Cloud. So all the data is going into the cloud right now. So actually, if you look at the future of growth of the data, it is going more and more into cloud. And edge is something in between. So for example, if you have a lot of smartphone devices and it's all that data is getting processed at a mobile tower, that's what edge means. But that's generally a smaller portion of data creation. Like I said, future is all in the cloud. That's where the most majority of data is going to go over time. Now, the point is that data creation happens because of existing applications like these things, as well as new applications that get created regularly. Like smartphone did not exist 15 years ago. Digital cameras did not exist 20 years ago. All these things come into existence over time because there's a demand for it, and then there is a supply for it. So every now and then a new application is created. It's hard to predict, but it keeps on happening. And this exponential growth of data has been happening for a long, long while and will continue to happen as long as human civilization is here to stay. This actually is part of human civilization growth. The reason why we become technologically advanced in all aspects of our life is because of this. This goes along with that. If this is not happening, human civilization is also going to cease to exist, basically. In order for us to continue to grow the way we're growing, this is inevitable. What will cause this? I cannot predict. 10 years from now, will there be another application? Probably. Which one will it be? I don't know. But I can guarantee to you this trajectory is not going anywhere as long as human beings will exist on this earth. So now, speaking of new applications, obviously you have to talk about AI. So ChatGPT is the new phenomena that many of us have been explored to. So let's think about how this new thing that has been happening is also ultimately leading to data generation. So I won't go into too much details here, but when we talk about machine learning, the way machine learning works is that you need to provide some input data. So let's say you take an example of a bunch of pictures, and you want to create a model to say, identify which one is a dog, which one is a cat, which one is a horse. The way it would work is that you supply all these input pictures, and pictures have information in it, right? So when you see, hey, this area is a bit dark, this area is a bit white, these are information, right? So those are inputs that go into the model. And then there's an output is this a dog, is this a cat, or is this a horse? And then you train the model on this, and there's a neural network in between which connects an input to an output through these equations, which are matrix multiplication equation. And if you train the model in it, the model will eventually figure out all possible connections between input and output, all possible equations that can exist, and eventually after that, once the model is trained, all you need to do is give an input and it will predict an output. That's, in a nutshell, what machine learning model training looks like. So what has been happening? What is new with ChatGPT? Why is suddenly everybody's talking about it, even though AI/ML has been there since 1950s, right? Nobody knew about it at that time. Nobody was talking about AI/ML in the 1950s except the hardcore experts. But now everybody's talking about it. So what changed? What changed is that the size of these models, right? These weights, if you look at this equation, matrix multiplication equation, the amount of nodes with which these things connect, and how many weights do you have, which is basically a multiplier of this here, that has been exponentially growing. So this is a plot of, these weights are called model parameters. If you plot model parameters versus time when that model was created, for a long, long while, all the way up to like past couple of years, it was still growing exponentially, but doubling every 1.5 to 2 years. Look what happened since the advent of large language models. It has just skyrocketed. It is still exponential, but with a much, much, much steeper slope. So what was doubling every 1.5 to 2 years is now doubling every 3 to 5 months. So just to give you a couple of examples, by the way, your ChatGPT-3, GPT-4 are right here. ChatGPT-3, the GPT-3 which it was based on, had about 175 billion parameters. 2 years later, GPT-4 comes, it has 1.75 trillion parameters. 10x jump in 2 years, okay? And so if you plot that trend, it's about doubling every 3 to 5 months. So this, again, is data. These model parameters are data. And today, the AI systems are like this. You have a memory chip that stores these parameters, which today is mostly DRAM, HBMs, high bandwidth memory. And you have a compute chip, which is GPU. I think all of you might have heard about GPU, NVIDIA, $1 trillion company. So the data keeps on going back and forth between the memory chip and the compute chip. Compute chip is where all the calculations happen, these calculations, weighted multiplication. But all the information, this weights values are stored in the memory chip. This is how today current AI systems are designed. Now there's a problem because the models are growing very rapidly in size, as you can see. And the memory chip used today is DRAM. And DRAM, I'll talk about it on the next few slides, is not very high capacity. If you buy a typical laptop, your DRAM is 16 gigabyte. And your SSD is 1 terabyte. There's a huge difference in capacity abilities of DRAM versus flash chip. So DRAM is just not able to keep up with this model parameter growth rate. And this is another opportunity for flash to store model weights in there. The other opportunity that exists here is this data has to keep going back and forth between the storage chip and the compute chip. And this consumes energy whenever you have to move data. So if you can do in-memory compute, that means instead of transferring data to GPU every time, if you can do computation here, at least some portion of the computation, that can significantly improve the power consumption and the performance of the AI systems as well. So both these areas, the in-memory compute as well as storage of these model parameters in the flash, are hot areas for flash, which are another application of new data storage, basically. Like I was saying on the prior slide, it's hard to predict what will be the new area next time that will require data storage. But they keep coming, And AI/ML is just the latest one. Yeah. All right, then moving on. So now I want to jump into flash memory. So I think so far I've been talking about data growth, the new applications that are causing that. But again, now I want to talk about how do we store that data and where does flash memory come in there. So before I talk about flash memory, I want to introduce memory, right? Flash memory is a type of memory, but there are other types of memories as well. So when you think of memory, a very common way to think about memories is what we call memory hierarchy or memory pyramid. So the bottom of the pyramid is typically things which are extremely dense and they are very high capacity, terabytes or more, but they are quite slow. So hard disk drive, for example. Hard disk drive, you can buy hard disk drive up to 10 terabyte or more, but the latency means if I ask it to do something, how quickly does it do it? So if I give it a command, hey, go read that data, when did it give me that data? That's what latency means. So you can think of it like performance, read performance. So latency of hard disk drive is in 10 millisecond domain. The higher up you go in this pyramid, the density reduces. So you can see NAND flash is right here. Density is almost 10x lower. So capacity and density both go hand in hand. It's lower, but latency improves. And the more higher you go, the more this trend becomes stronger and stronger. So NAND flash, what is so unique about NAND flash? The other aspects of memory, apart from the density and latency trade-off that I'm talking about, is the volatility of the memory. Volatility means if the memory loses power, does it still retain the data? So if you take a USB drive, you store something in it, you take it out of the device, is the data still there? What do you guys think? Still there, right? That means it's a non-volatile memory because even without power, it is able to sustain data. Try doing that with your DRAM. Try switching off your laptop and whatever was in DRAM goes away. That's why it takes time for laptop to boot up. Okay? So DRAM and everything else on top of this pyramid are basically volatile memories. The red dot means volatile. That means it constantly needs power to retain data. You lose power, you lose data. But the non-volatile memory are the bottom two here, NAND flash and hard disk. So NAND flash has a very sweet spot that is non-volatile, fast enough for most consumer applications, and still dense enough, much, much denser than DRAM. So it's a very sweet spot it sits in. And that's why it has been the technology of choice or a chip of choice for vast amount of data storage, especially in the consumer space. So moving on, I showed you the exponential growth of data on the prior slides. Now I want to show you the exponential growth of NAND flash memory, bits stored on the NAND flash memory. So this is NAND industry bits. So this is not data. This is showing how much data is stored in a NAND flash chip. So you can see this is also exponential in nature. And this is a log scale now. So it's almost linear. And it's doubling every 3 years. And you as a consumer can feel it. If you bought a laptop 5 years ago, chances are you bought 128 gigabyte SSD maybe. Try buying it today. You'll get 512 gigabyte SSD or even 1 terabyte SSDs. And this is going to go on and on and on exponentially. But the key point is you cannot have this exponential growth in capacity if it's not tied up with exponential reduction in price. The same SSD you were buying for 128 gigabyte 5 years ago, you're buying it for the same price today with 1 terabyte. That is happening because of the right plot. The average selling price of NAND flash, so dollar per gigabyte, has been exponentially coming down. This is again log scale. Typically, right now, it's operating around 15% reduction a year. This is necessary for this to happen. This cannot happen if this did not happen. Because if price is not reducing, nobody's going to pay trillions of dollars to store all this data. Your laptop will cost $10,000 if this was not happening. So these two things have to go hand in hand. And the technologies that drive this drive both these things together. So let's jump into how this was done. What technologies or what scaling strategies enabled this to happen? Exponential growth in the capacity or density and exponential fall down of the price happening together. So basically, in a nutshell, it's following Moore's law. So Moore's law is scaling of that you keep shrinking the minimum device in the chip to smaller and smaller dimension every year. That's what Moore's law dictates. Basically, exponentially slow down of the minimum dimension of the chip. And this is how that has been going on in the NAND flash industry. So back in 2001, the NAND flash chip that was produced was 1 gigabit. And over time, we have been scaling this, what you see a small number here, 160 nanometer. This is the minimum dimension of the chip. The minimum dimension of the chip has been going down, 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 keep on going down. From in about 20 years, it has gone down from 160 nanometer to 1Z, which was 15 nanometer. 10x reduction in the minimum dimension of the minimum feature size of the chip. And that enables you to store more and more cells in the same chip. So same chip that had 1 gigabyte before now has 128 gigabit. So like I was saying on the prior slide, these two things happen together because in the same chip size, same amount of chip, which means I'm spending same amount of money to make it, I'm storing 100x data now. And that's why the price reduction on a per gigabyte basis have been coming down. At the same time, the capacity and density have been coming up as well. So it's basically following Moore's law. And overall, this has enabled us to go 1000x cost reduction in 20 years. 1000x. This is incredible. This does not happen anywhere else outside semiconductors. This is the beauty of semiconductors, that this Moore's law, it keeps on churning and keeps on generating more and more bits at a lower, cheaper and cheaper price. This is why our technology, all of us have laptops in hand, all of us have phones in hand because of this. If this was not happening, many of these things would be reserved to the elites, right? We won't have access to it. And then you can see the era, it used to be 1 gigabit, 10 gigabit, 100 gigabyte, and now we're in the terabyte era now. So most of the SSDs you'll buy will be terabyte now. So also a paradigm shift happened back in 2016. I'll touch more on that between 2D NAND flash and 3D NAND flash, but just hold on that. I'll come back to that. So now I want to dig one step deeper into understanding how the scaling happens, what are the challenges we deal with, where does the physics come into play, right? So this is not just magic, right? It takes a lot of hard work, a lot of innovation, a lot of science knowledge to make this happen. So I want to introduce you, without going into too much details, I want to introduce you how the basics of NAND flash memory cell works and why is scaling so difficult and why you need constant innovations to deal with those scaling challenges. So let's introduce a basic MOSFET device first. A MOSFET device is basically a gate where you apply some voltages. It's a 3-terminal device. So you have 3 areas where voltages can be applied. That's what 3 terminals means. You have a source, you have a drain, and a gate. So the MOSFET device simply means that by changing the gate voltage, you can modulate the current that flows through this channel. That's what defines a MOSFET device. But MOSFET device is one fixed threshold voltage device. So threshold voltage means the voltage at which this current starts to conduct. So it can go, it's a switch basically. It can go from off to on, but it is only one voltage at which it will switches from on to off to on. But in a memory device, a memory needs, memory should be able to program or erase, which means you should be able to switch it and keep it in that state without power. That's what memory needs for non-volatile memory. So a simple MOSFET cannot do it. We need switchability, whereby changing something here, I can switch it from a 0 to a 1. That's what differentiates a memory from a MOSFET. But before I go into memory, trivia number one. The co-inventor of MOSFET was a gentleman named Mohammed Martin Atalla, okay? Born in 1924, so long time back. Does anybody know which school did he do his grad school from? Oh, many hands. All right, let's go with you.
Was it here?
Yes, all right. You got a USB, right? Yes, so he studied here in Purdue University. He did his MSc and PhD here. So you all are fortunate here to, to be in this school. I mean, it's an honor to study in this school. It's a great legacy that the school has with many inventors who have created the whole industry in not only semiconductors and more than that. So, yeah, thank you for getting the answer right. So going further, now I was describing how you start with a MOSFET and create a memory cell out of it. So like I was saying, a MOSFET is a fixed threshold voltage device. It switches at a given gate voltage. But this is not sufficient for you to be a memory. So what you do is you take this gate high, separate the gate here, insert what we call charge storage layer. And with this charge storage layer, depending on how much charge you store in this layer, it can switch from a 0 to 1. So basically, by modulating the amount of charge that you have, you can decide whether this cell is going to be a 0 or a 1. And let me explain that a little bit more here. So this is the same diagram here. So you have the gate and then charge storage layer here. So if you start with an erased cell, one cell, it had no charge in it, or let's say neutral charge. If you apply a high programming voltage, almost 20 volt type of level, and you can inject electrons into the charge storage layer, and now these electrons act as create a negative field there, which causes its threshold voltage to go up from a lower voltage to a higher voltage, because now the gate has to apply a higher voltage to drive the same amount of current, because it has to fight the effect of these electrons. So this is how you switched a cell that was 1, which means when you read it, it conducts currents, to a cell which was 0, which becomes a 0, which means if you read it, it does not conduct a current. So this is how you can switch a 0 from a 1, and this is what defines a memory. So that's what a flash memory cell basic operation looks like. But in order for us to create these gigabit, terabit type of arrays, you can't just have one cell. One cell gives you 1 bit. But we are talking about terabits, okay, trillions of bits, or more than trillions of bits. So we have to talk about array of cells. So when we talk about array of cells, if one cell is here, other cell is here, it's surrounded by, in this case, 8 cells. So you have to start talking about cell proximity effects, because there's crosstalk between the cells. So if you program this guy and you start program this guy, it affects the threshold voltage of this cell. So these proximity effects is the fundamental scaling challenge that we face. So when we go from, in that prior slide I was showing 160 nanometer to 15 nanometer, this is that space I'm talking about, the space between the two adjacent cells. The narrower you make it, the higher the proximity effects become, and the harder it becomes to control the threshold voltages of these cells. So this is a fundamental scaling challenge. So ultimately it comes down to capacitance between these two charge storage layers. So if you can reduce that capacitance, you can reduce the proximity effect. So how do you reduce capacitance? So capacitance, if you remember the formula from your school, is dielectric constant multiplied by area divided by the distance between the two. So if I will give you a problem and I said, hey, I have a lot of capacitance between these two nodes, I want to reduce it. I want to introduce some new material in between that to reduce that capacitance, so I can reduce this cross-coupling effects. How would you do it? Does anybody know a dielectric or something that has a low dielectric constant? Yes? Vacuum, absolutely. You got another one. Second USB coming your way. Absolutely. So yes, air gap. So that's what the industry did. As the proximity effects kept on increasing, you can see we went from 160 nanometer, 90 nanometer, 24 nanometer, kept on going up almost exponentially, because the spacing kept on reducing. So the proximity effect kept on going up. And it was become unsustainable at some point. So this is where innovation came in, and the innovation was introducing air gap technology. Basically, this is vacuum. This is dielectric constant 1. It's the lowest dielectric constant we can get in regular materials. So by doing this, you can see what happened. Even when we scaled from 24 nanometer to 1x, which was 19 nanometer, the proximity effect did not become worse. Why? Because we introduced air in between, so we reduce the capacitance of that space. So this is an example of innovation. And you see your knowledge of science, basic knowledge of science comes into play when you innovate these things. This is why we need such innovations from people who study these type of technologies, these type of science and math, so we can solve these challenges. And this is necessary for us to do scaling. You cannot scale if you don't solve these challenges on a routine basis. But so this is an example of physical innovation, where you change something in the physical structure of the cell to deal with these scaling challenges that I talked about. There are also electrical innovations as well that happen. So when we think about flash memory cell, you can modulate how you electrically operate the cell as well, the order in which you program things. So I won't go into too much details on this, but this is another innovation of electrical innovation, where by changing the order of programming of cells, you can mitigate the proximity effect. And the benefit of that is shown here. As we kept on scaling from 1x to 1y to 1z, you can see the proximity effects grew, but not at the same pace they were growing before, because we came up with more innovations now on the electrical side. So these are just two examples, these are tip of the iceberg, but innovation is a constant state of existence in semiconductor space. If you don't innovate, you die. It's a moving target we are chasing. Everybody is trying to innovate. It's a race, and whoever does it first wins. So these are just two examples of hundreds of innovations that the industry has come up with, including us. Yep. So now when I just go to near the end of my talk, talking about future of NAND flash. So like I showed here, the proximity effects kept on going up and up. We came up with innovations, but at some point you run out of steam, right? At some point you're like, I need to look for a paradigm shift. I need to break this barrier of proximity completely, make a fundamental change in NAND architecture, because it's just not sustainable to keep scaling at this pace. You can scale it, but just it takes too much time to solve all these issues, so it's not economically viable at that point. So when the industry reaches that point, then there's an opportunity for new technologies to come. And new technologies can be a brand new technology that completely replaces NAND flash, or it could be a variant of NAND flash with a major architecture change. That's what happened in 2016 to the NAND flash industry. So 3D NAND era began in 2016. So what is 3D NAND? So you see this that I described on the prior slides is a planar NAND. You have one layer of memory cells, just one layer. But like I was showing, if you kept on scaling this, the proximity effect kept on going up, and at some point it was just not manageable. Even with all the great innovations that we all came up with, it just was not good enough. So at some point we had to completely switch the NAND architecture. So what we did was we took this cell, so this is the planar cell, all located on one plane, right? And we flipped it in 3 dimensions. And now it introduced another dimension of scaling. So in the original case, it was everything on one plane. So all we're trying to do is squeeze, 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 keep on squeezing the cell. But then we can't squeeze it anymore. It's like, okay, how about this? What if I create multiple of these layers? And I can still keep squeezing them, but I have multiple of them. So now I have 2 dimensions of scaling. I can squeeze things laterally, which we can continue to do, but I can stack up layers as well. And that unique dimension of scaling gives you extra knob for the scaling, basically, to increase density and so on. But the good part as far as proximity effect is concerned is that once you do this, and this is how that cell structure looks now, you have layers of cell. Each of this plate is one layer of cell. The good thing is these layers are metallic. And what is good thing about metallic? If I put a metal in between 2 memory cells here, what do you think happens to electric field lines between this? Does electric field lines go through the metal?
Not well.
Not well. Actually, it does not go at all. Does not. So basically, there's going to be no cross coupling between the two, because the electric field lines cannot go through the metal. So by doing that, we completely eliminated a cross coupling effect. This cross coupling effect. There's still some cross coupling effects in this dimension, but across this, it completely went away. So what that did to the overall proximity effect is a major drop in proximity effect from where we ended to where we started. And our 3D NAND is also multiple generation. BICS is our proprietary name for 3D NAND, bit cost scalable NAND. We have come up with, in this chart, the 3 generations of it. You can see it took a dramatic fall. So we rewind the clock all the way 20 years back. That's what this architecture change did. But these massive changes are not easy. Otherwise, you might say, hey, why didn't you do this before, right? It's such a good thing. Why didn't you do it before? It requires a lot of money. We have to buy new tools in the fab to create this type of 3D NAND technology. You have to etch these whole long trenches now. So it totally transforms how you manufacture the technology. So these are not easy changes. This is a once in a 20-year event is what happened in 2016. But it can happen again as long as there is a need for it, right? So at some point, 3D NAND will also run out of steam. And then somebody else will invent something else, whether it's another architecture of NAND, whatever you want to call it, or maybe it is some other new technology altogether. But these things don't happen that rapidly. So I think 3D NAND is here to stay at least for the next 10 years, in my opinion. So 3D NAND was a major architecture change. And like I said, the main scaling knob that we have in 3D NAND now is to keep stacking up layers on top of each other. And the more layer you stack, the more density of chip you get. Because every layer is one bunch of memory. The more layers you add, the more bunch of memory you have, the more density you're creating. And starting from 2016 to now, we have come up with BiCS2, BiCS3, 4, 5, 6, 8. We started with 48 layer in terms of mass production. Today, we are shipping 218 layer. That's state of the art today. I believe within the next 10 years, there'll be a 1,000 layer 3D NAND product, 1,000 layer. I cannot see beyond that. So this ever increasing number of layers also requires innovation, because the more layers you stack, the harder it becomes to etch these layers. And the longer the channels become, the lesser the cell currents become. So again, innovation is constantly needed to keep up with this as well. It's not that 3D NAND solved all our problems. Yes, it solved the proximity effect problem, but there are some other challenges that 3D NAND introduces, and that again requires a constant state of innovation. So I want to end with one last slide now, which is talking about further dimension of scaling. I will just touch on it and talk about different problems that it creates and different challenges it has, and hence there's more room for innovation. So we touched on two aspects of scaling already. One was vertical scaling, which is stacking up more and more layers, which I showed on the prior slide. The other one was lateral scaling, which means every layer, how much can I squeeze memory in? Those two things I explained. But there are other scaling dimensions also for 3D NAND. Another one is architecture scaling. So when we talk about NAND flash, I focus more on the memory cell. But somebody has to generate all these voltages to drive these memory cells. The 20 volt to program, to erase, to read. This requires voltage generation. Those voltage generation happens in a CMOS. And those voltages are delivered to the cell array through a circuits, basically. So when we talk about NAND architecture, we have how you place your CMOS and array is also another dimension of scaling. So previously, we used to have what we call CMOS next to array. So this is the white thing here is CMOS. The red thing here is the cell area. So it was CMOS next to array like this. But after that, now most of the industry has moved to CUA, CMOS under the array. So you can see it is hiding under the array now, which obviously helps you with the density because it occupies less footprint. And now the one that our last generation of NAND that I showed on the prior slide, this one, BiCS8. So you see there's something special going on here at the bottom. That special thing is CBA. This is CMOS bonded to array. So this is not one silicon wafer anymore. There are two wafers, one wafer for CMOS, one wafer for cell array, and you bond them together through copper bonding. And then using that, you can also increase the density of the chip. And down the line, we envision multiple wafer bonding happening. You could be bonding a 200 layer wafer with another 200 layer wafer to make a 400 layer along with the CMOS. That's another path of scaling that we envision going forward. And all of these have their own challenges, right? So when you talk about vertical scaling, I was saying structural strength, how tall the stack are. Like skyscrapers are only so high, right? You cannot make a 1,000,000-story skyscraper because at some point it just falls apart. Same thing happens in the 3D NAND flash as well. The taller you make it, the weaker structure becomes. So we have to deal with that structural strength challenge. Then processing time keeps on going up. The more layers you stack up, that increases cost. Cell reliability challenges are there because this taller stack makes the cell currents lower, which introduces reliability challenges. Similarly, for this scaling path as well, process complexity increase when you try to hide CMOS under the array, or wafer cost will increase when you have two wafers instead of one. And finally, I want to talk about logical scaling. Logical scaling, when I described the flash memory cell, 0 and a 1, one cell stored 1 bit. But through innovation, what we have been able to do is that how can we store more than 1 bit per cell? So that's what logical scaling means, and that is done by storing multiple possible threshold voltage distributions within a given space. So using this, we can, SLC means single level cell, 1 bit per cell, MLC means 2 bit per cell, TLC means triple level cell, 3 bit per cell, QLC is 4 bit per cell. So within the same physical space, instead of storing 1 bit, we are storing 2 bit, 3 bit, 4 bit. That means the density multiplies. And so today, mainstream technology is TLC, 3 bit per cell. Any random SSD you pick off the shelf is going to be TLC. But slowly, industry is migrating to QLC. And that's another 33% jump in density at the same price, no price increase. So this is another logical scaling knob that we have that we are constantly keep using. And like I said, slowly industry is migrating to QLC, and hopefully one day we'll see PLC as well. But the point I want to end with is that all these scaling opportunities, all these scaling paths have challenges. Many of them we have solved over time. Many of them still remain, and they keep increasing as we make our scaling more and more complex, start to squeeze in more and more information in the same space, and that's where constant state of innovation is needed. So there's plenty of opportunity for innovation in this space, and all the things you're learning here in this course and over the next 3 years of your education here, and hopefully more beyond that with grad school, this is all going to come into play. So we really look forward to all of you to contribute to the broader industry and WD as well to keep up this human civilization going. Human civilization depends on this, depends on these innovations. So we really hopefully see contribution from you in the long term as well. Yeah, thank you. So.
Thank you, Deepanshu, for the great talk.
Sure.
Really eye-opening for really what's going on behind the scene, right, to fulfill the world's data storage needs. So we are open for questions for the live audience before we revisit some of the online questions. Anyone want to give the shot for the first question before we round off the USB drives?
Oh, yes.
When a new PCIe protocol is introduced, like PCIe 5.0, what changes happen in the SSDs that allow them to go at faster speeds? Is it stacking more layers, or is there like a fundamental difference in the 3D NAND?
It's a good question, yeah. So I did not touch too much into this, but when we talk about this CMOS, the pace at which the CMOS interacts with the controller. So in a typical SSD system, my talk was mostly focused on NAND flash. But when you talk about a product, in an SSD, for example, you have a NAND flash chip and a controller chip, or ASIC as we call it. And those two things talk at a certain time, at a certain speed. So when you increase the PCIe interface is the ASIC to the host. So host means CPU in a laptop case. So when the speed of the PCIe interface, which is the host to the controller interface, goes up, then the interface speed between the NAND and the CMOS starts becoming bottleneck. Because this ultimately data has to flow from the NAND to the CMOS, to the ASIC, to the host CPU in this case. That whole chain has to be there. So if you speed up one part of that chain and you don't speed up the rest, it's not going to work, right? The bottleneck is going to come from the other one. So as the PCIe Gen interface goes from Gen 4 to Gen 5, maybe Gen 6 one day, we have to keep speeding up our CMOS to the NAND to the ASIC interface as well. And we call that toggle mode speed. It's the speed at which the data goes from NAND into the ASIC. So every generation, we increase that toggle mode speed. So today, the state of the art in the industry is around 3 gigabyte per second. And when we go to PCIe Gen 5 or Gen 6, we plan to increase it to 4.8 gigabyte per second. So there's constant CMOS innovations to enable that as well. Today in the talk, I mostly touched on the cell innovations and the array side, but CMOS innovations are also happening hand in hand with that. So that's what happens. CMOS innovation happens to raise the speed of interface between the NAND and the ASIC to keep up with the PCIe generation interfaces. Yeah, sure.
So I guess really requires the whole ecosystem to innovate together.
Exactly.
Next question.
Yeah.
Are we interested in SSD storage area for the future? Or what determined you want to work in this area?
Yeah, so I think, like I was saying, when I started my career, I didn't even know I wanted to be in semiconductors, to be honest, when I began. When I was your age, I just wanted to learn about physics. Physics was interesting to me. So I started engineering physics. And engineering physics is a very, very wide area. So it can branch into all sorts of things, right? So, and when I took my, I think, second year course, I believe, there was a semiconductor device physics course, which I really liked. And that's when I started to think, hey, this chips area is very exciting. I want to go into that. And I didn't know NAND flash at that time. I didn't even know what that was. All I knew was semiconductors and chips, and this is the future. And then I just wanted to go into semiconductor space. And then I took my grad school into that space. So the NAND flash just came out randomly, right? I just happened to find a job in SanDisk. But I knew I wanted to be in semiconductor space after I took the course of semiconductor device physics in my second year. So that's where it all started from, in my opinion. Yeah. Just like you are doing today to be in this course. Yes.
Do you work with or design like clouds or companies that design cloud storage areas, like where I guess all the fiber optic cables lead like memory and stuff? Like how does that collaboration work within your company? Are you more just like private party where you sell your products, or is it within those centers as well?
Yeah, so when we talk about cloud, I think there are some major big players in the cloud, like Google Cloud, Microsoft, Azure, and AWS. So I think there are three big ones, and there might be a few other ones as well I'm missing. So all of them are our customers. So they architect the whole system, the cloud companies, but we work very closely with them on the SSD aspect of it. When we talk about cloud, there's more than SSD, right? So it's a whole system of data management. SSD is one piece of it. So we work closely with them. They're all our customers on, hey, what kind of specs do you need for SSD? How fast do you need it to be? What kind of density you need? And of course, we get requirements from them and we try to meet them. And then we satisfy the SSD element of it with them. Yeah. Yes?
On the slide with the 1000x increase in density,
Yes.
it said X2 and X3. Now,
Oh, yes.
What does that mean?
So that's actually the logical scaling that I talked about at the end. So good question. So X2 is the 2-bit per cell.
Yeah, okay.
Yeah, X3 is the 3-bit per cell. I don't quite show X4, but we do have X4 as well in this technology.
Okay.
Typically, we make multiple chips in a given generation. So generation means like 218 layer is one generation. We have X3 chip, X4 chip, both. Yeah. So it's number of bits per cell. Yes. Yes.
So CPUs have really not been progressing as much because of thermal issues recently. How come NAND is still able to scale? Like, what are you all doing with thermal considerations that it's still scaling well?
So I don't know too much about CPU scaling, so I cannot comment too much about that. But first of all, I would say energy consumption is an issue for NAND also. This is something we keep on improving every generation. So there are multiple things that improve every generation. Like generation means all these are generations. So of course, density is the most visible one, right? So you can see 1 gigabit to 1 terabit, 1000x movement. But we constantly improve performance, power as well, and cost when we do this thing. So there are constant innovations to improve power as well. One thing is that in memory cell, what's happening is that when you scale the memory cell, let's say you take a 150 nanometer cell and you shrink it to 15 nanometer, the number of electrons that go into the cell, when we talk about energy, you really bring it down to the fundamental thing. The fundamental energy consumption in the memory programming is electron movement. When you have to move one electron, let me go to this. When you have to move one electron from here to here, it consumes energy, right? So that's the fundamental source of energy consumption. There are other sources too, but that's the big one. When you make the cell smaller, the amount of electrons you need to move into the cell also reduces. So that's why naturally the energy sort of stays constant, at least for cell programming aspects. There are other reasons why energy goes up on the CMOS side especially, but that's where we need innovations to come up with. But from a pure cell point of view, the beauty is that scaling naturally takes care of energy consumption because number of electrons scale with the amount of size of the cell. Yeah.
I guess just want to add one point. Borrowing Deepanshu's nice slide on this memory hierarchy, right? You see the latency, right, accessing the storage is much higher than your, for example, accessing DRAM and versus accessing CPU, right? So your CPU is getting hotter and hotter because you are clocking that very fast, right? And then the power dissipation is proportional to the frequency you are running. right? If you keep your CPU at a really low frequency, you'll probably get a cool down CPU. And similarly for the NAND flash, right? The memory in general is cooler than the logic, and for the storage is even more, right? So but again, the energy efficiency is also one key point, right? So reducing the total energy is really helpful. More questions?
Like over the past couple of weeks, we've had a bunch of like CPU companies and manufacturing companies coming in, and they've been talking a lot about like the sizes of the different process nodes. So CPUs are getting made on like 3 nanometers right now. What process node is NAND made on?
Yeah, so the whole concept of process node on a cell is gone with 3D NAND. So up to 2D NAND, the process node was the one which I showed here. So this number that you see here, 160 nanometer, 130 nanometer, all the way going down to 1Z, which was 15 nanometer, this was the process node. That was all about making cells smaller and smaller and smaller. But now in 3D NAND, it's more about how many layers can we stack. So the whole concept of process node, which comes from lithography, is not that relevant in 3D NAND anymore. It's just a paradigm shift happened. Yeah. But our CMOS technology, which might be closer to CPU, is way bigger than CPU. Our CMOS technology typically is run around 40 nanometer, not 3, 40 nanometer, yeah. So I think it all depends on what the needs are. Our CMOS technology does not need the speeds that CPU needs. So making these 3 nanometer things costs a lot of money. So you do it only if necessary. We don't need those speeds that CPU needs. Yeah.
I noticed that you didn't have like a separate wire going to every memory cell. How are you accessing each like specific memory cells, even with like just limited number of?
Yes. So so this red thing that you see is metal plate. So whatever voltage we apply here will be felt by all these cells. So all of them at once in terms of the voltage that they feel on the gate. So this plate acts as a gate for these cells. Now we do have separate voltages on the top of these things, which is not shown here, which is individual for every cell. Yes. Yeah.
I guess one last question from the online discussion. With the rapid advancements in data storage applications, what emerging skills, in your opinion, are critical for new graduates like them, aiming to enter this industry?
Take this course. That's one of them. But I think, obviously, I think Purdue has a great semiconductor curriculum. So I would encourage, if you want to be in semiconductor space, to take those. Take projects with your professors. Doing hands-on work is always helpful. But one thing that's most important is remain curious, because really innovation does not come by studying a bunch of stuff. It helps, but that's not sufficient. Curiosity, being passionate in that area, remaining motivated to do something better than what other people have done in the past is what it takes ultimately to succeed.
All right. Thank you, Deepanshu, again.
All right.
It's a really great talk.